Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
His CEO actually interned with us a few years ago, so that's how small this world is. But it's a pleasure to have Sean here. He's going to tell us today about some work he did during his PhD with his advisor Wilson Spear on designing a little language to build better components. So, Sean.
Okay, so this talk is going to be about language design, not program analysis. So just to be clear on that. Actually, the language is not a language to implement components, but to glue components together. So here's the idea. Here's the objectives, and the language is called superglue. And what we're trying to do is we're trying to simplify the development of interactive programs, or programs with components that generally interact with each other as opposed to running in pipelines. And we're going to focus on the glue code for these programs. And what this does is that we really de-emphasize the algorithmic complexity of the code, and we focus more on integration issues. And we don't worry about how the components are implemented. We just assume they can be implemented in a standard conventional programming language. Okay? So basically, interactive programs are most commonly used to build sort of user interfaces. And the sort of architecture that's done under is that you might have some data to be viewed, like a mailbox or an email system, and you might have a user interface to view that data. And the idea is that the data source is modeling the data, whereas the data processor is viewing the data. And this is sort of a part of the model view controller design pattern. And to get these components working together, so we have components that provide models and we have components that provide views. To get them to work together, we have to write out some glue code to get these components to call each other's functions. And generally, this glue code is implementing sort of two kinds of behaviors in these applications. One is for the view can request the current data from the model whenever it wants to. So it sort of says, OK, what value are you now? And the other kind of communication that goes on here that the glue code establishes is sort of event-driven notification communication. So it's basically when does your value change? So the model will say, my value changed. Now you have to update your reasoning about my data with respect to that change. OK? So these changes also here are, and the request current from the user interface to the glue code, and the notify change from the models to the glue code, they're in the wrong direction because the glue code is setting everything up. So you can't have your components calling the glue code. So what you do instead is you install various callbacks to get these components to communicate with each other. And so these callbacks are sort of difficult to write. And not just the callbacks, but just getting the components to communicate are difficult. It's difficult because the component interfaces don't match each other, right? So we generally have objects with a bunch of methods, and different objects have different methods, and they don't use compatible APIs, basically. So what happens is that your glue code has to go ahead and adapt each object to each other's interface. And this is especially problematic at the level of event handling. So we have these methods down here. It says, for a user interface table, we have the table changed method that notifies the table that its view data has changed. And for an email folder, we have message added and message removed functions that are called when data changes. You register a callback, it calls, and you implement these callbacks to call the table. And this code is sort of difficult. It's basically you have to do a lot of work getting these APIs to work together. And that's one problem with glue code, and that's the problem I'm trying to solve in this language. And the other problem, is composability. So this is a little bit more trickier. Basically is that you have a lot of different components, and they're providing a lot of state. They're each providing their own state, and you want to get this state to work together. Do you want to compose the state into sort of compound states that are then viewed by another component? So what we have here is sort of a composability problem, which is to take the folder that's selected in the UI tree view and say, if that we want to view the folders of this messages in a UI table view. And to do that, we have to write a lot of more glue code. And I'm not going to show you the glue code. I just have a flow diagram of what it looks like. So you start off by installing a tree selection listener on your user interface tree. And you go and implement a callback that when it's called, you're going to uninstall and install a message count listener on an email folder. And you're going to implement another callback that takes messages when they're added and removed, and you're going to update the table accordingly. So writing this code, let's say maybe 30, 40 lines of Java code to implement this behavior. So the solution I'm going to propose here, and actually follow through with a language, is we're going to use sort of these abstractions known as signals to sort of facilitate communication between components. Right? So a signal is sort of like we call them time-varying values, but basically they have a value, and every time you look at it, it's going to change. So they vary continuously with time. But more practically speaking, a signal is just an abstraction that encapsulates behavior related to the communication of state. So it's going to have, within the signal abstraction, we're going to have facilities for getting the current value and for installing and uninstalling event handlers that are called when the value changes. Right? And so once we've had this abstraction, so it's basically an API, you can think of it. But the idea is that the language runtime understands this API and is able to use that in the construction of what we call circuits that can then compose these abstractions. So the first thing is we have the signals. You write your components to the signals, and your components become compatible. The second thing is that we have circuits that allow you to compose signals together, which allow you to compose state. Okay? And so this is basically an architecture of the language. So we have components. We're going to just implement them. And the prototype is using Java. We use and implement signals in Java code. We call them drivers that translate between super glue code and Java code. And then outside, the glue code is basically expressing a bunch of circuits that facilitate communication between these components. Okay, so that's.
So, Sean,
sorry.
super glue is the language for describing those circuits.
Yes, basically it's for building circuits.
And the interface points, those drivers are in Java?
The components can be implemented in Java, or they can be implemented in superglue. And then you have to translate between the two languages, sort of like a native method interface that you would have in other languages. So it's...
Right. So that's done by the program?
It's done by the component implementer.
Right.
So I mean, if you want the component to work, you have to, in the language, you have to write these drivers that make the component's APIs available. And that's a little bit trickier than...
But it's much simpler than actually having to do that whole circuitry of the component connection in Java.
So the idea is that you are implementing you're implementing a component that will be reused many times. So if you're doing a user interface library, it's reasonable to expect that you'd have thousands of programs depending on your user interface library. So the driver's cost is amortized over all those uses of the library. Now, if you have a one-off application, you have legacy code that you want to reuse, then you have to write this complicated driver that might not make it worthwhile. You can also write some simple components in superglue. So it's only these complicated components that need to be written in this language. So there's a problem with this connection model. It's not very scalable. So it works great when we're making a connection between two components, one connection between two components. We just say, okay, connect these components together. But, applications have a large number of connections and possibly an unbounded number of connections when you get into data structures like lists and trees. So the unique contribution in our language is that we are applying object-oriented abstractions. We're combining signal abstractions with object abstractions to get object-oriented signals. And basically, we have a way of expressing in circuits how you express connections by type between two objects, as opposed to expressing connections individually.
Sorry, so I think I missed that. So what wasn't scalable about the architecture previously?
So the idea is when you're expressing. So think back to your. Well, let me just go back here. Sort of abstract, but when you're expressing how your individual circuits are. So if you're going back to your. I don't know if you have digital design logic class before, but you plop down chips and you express how those chips are connected, right? And if you have a few pins, that's okay. But if you have 1,000 pins or 10,000 pins, that's not okay. And you need some higher level of abstraction to sort of manage those connections.
Well, I'm trying to contrast this to well-known existing techniques from 10 plus years ago. So this is, I take it this is a sort of implicit negotiation system. And there's lots of ways of approaching this. I mean, you could build a kind of blackboard system, for example, right?
Mm-hmm.
Which you simply, the connections are totally implicit. So components send signals out, others just sit and wait for it. You never really hook up explicit circuitry. And the promoted benefit of that design has always been that it scales really well. You don't need to care how many components are listening for a signal or how many transformations are going on in the system. You can just file in all the components that you want.
Yeah, for some systems that actually works pretty well. For a lot of systems, though, you don't. That's not the right abstraction. So
what characterizes
this is you can think of this as another architecture. If you want to think it in terms of a software architecture, this is the model view controller architecture put into a language,
okay,
as opposed to a Blackboard architecture. So a Blackboard architecture works for some programs. It's got, you don't see it a lot outside of artificial intelligence and agent stuff, but it's not used a lot in user interfaces, for example. But it's another way of attacking this, is basically with a well-known architecture. And this is just another example of a well-known architecture that can be used sort of in a really large domain.
Okay, cool. So what characterizes the problem where that solution is appropriate as opposed to your solution? What niche are you filling that was unfilled before?
So I'm filling I said before that this is sort of model view controller architecture. So that niche has already been established, I think. And if you look at a lot of the object-oriented programming APIs, they use model view controller a lot. I'm not quite sure about specific Microsoft APIs, but Apple, Java APIs are all heavily biased to model view controller. So there's that niche. Is basically there's a lot of code out there that already sort of follows this architecture.
And for that niche, what you're doing is you're providing language abstractions to capture that.
Sure. And I should point out that this is not, signals are not my invention. I mean, this is actually, there's a Microsoft research even, Connell Elliott he's a language guy, and he did a paper on event-driven programming in Haskell. So I mean, signals have been around in Haskell for a while, and they're making their way into functional programming languages now. The difference between their work and my work would be basically the way it's being presented. Here I'm presenting it in sort of a language that's designed for ease of use, and the Haskell people are more interested in formalisms, and some other people have different needs. But basically, this is a combination of object-oriented and signal techniques. So basically, we're going to be able to abstract over connections like you can abstract over method implementations in an object-oriented programming. And I won't explain this. I won't explain this illustration right now. I'll get back to it later. But it's basically the idea is to clean up the connections. So you can express a few connections abstractly and get a lot of connections out in your executing program. So that's sort of the end of my introduction. The rest of this talk, I will just go through the language. Start out with signals. Just basically explain what those are at a basic level, and then go into objects, which is my core contribution. And then I'll kind of talk about how effective this language is via an evaluation, and then I'll get to my conclusion. So, signals. So this is sort of a simple program in superglue. What's going on here is that we're declaring two objects. We're declaring a thermometer object and a label object, which is a sort of a user interface widget. And we'll call those the model object and the view object. And we're basically attaching the current temperature to, as viewed through the thermometer, to the label. That should be text, not label. I don't know why. And what happens is that whenever that value changes, right, the label is going to change automatically. That's what signals do. Okay? So
that's not a sign.
that is a connection. So you're connecting two pins together. So I mean, you can think of it as a constraint, but I would you know, there's the advantages and disadvantages. Yeah. I mean, yeah. So yeah, it's basically a direction. So you're saying something that requires something is being connected to something that provides something. It's not necessarily like a constraint where you can take arbitrary variables of you know, and say that they're equal or greater than or something like that. It wouldn't work like that. You'd have to have an input and an output to connect.
I can think of this like a spreadsheet, where I'm saying this cell
Yeah,
was
it's like a function.
computed over here.
It's-
and if I change over here instantly without doing any work,
It's you know, you can think of it as a function, or you can think of it as a rule. I like to think of them as rules, and this is basically establishing something that can be used to prove what label is assigned to, or what value label has at any point in the program time.
Might want to use some other syntax.
Yeah, you know, yeah. This is the nice thing about assignment here is that.
I think giving it a third use because it never should have been given a second use.
Yeah, exactly.
I'm saying is a well-established precedent for mangling.
So I mean, there's advantages to using a different symbol. I mean, I've gone through these arguments with my advisor a lot. Let's put it that way. You know, there's advantages to using different symbols, and this would sort of make it easier for people, you know, in Java to sort of say, well, I can kind of think of this code like Java code, except it's continuous evaluation instead of, you know, sort of sequential ordered evaluation. But you know, I mean, a different symbol may make it look like Haskell, and nobody would go near the language. So there's a lot of things to consider. You can do that. You can connect things in cycles, and the program will blow up. I mean, you can connect components.
There's no fixed point in that.
No, there's no fixed point. This is basically, you know, you would create a feedback loop, and you would infinite loop.
And are there any
There's a type system.
And you don't static checking.
Not yet.
That there's no loops.
other constraints on the side effect?
Well, they're not functions. The idea is that, you know, they have to basically, something's providing data and something's consuming data, and that's the constraint. Now, inside the implementations of the components, they can do whatever they want with the data, right? But the idea is that they have this very simple API that they have to work through, the signal API. So, and there's no constraint system that prevents feedbacks from coming in. I mean, that's something we can add later. But, you know, right now we're trying to get the sort of the usefulness of the language established before, you know, looking at the other details, like, you know, not shooting yourself in the foot. So,
Is it accurate to say that there's some deterministic value?
no, definitely not. So that would be the other work. The Haskell work, they have a synchronous model of signals. So basically what they do is they evaluate for each individual time t, and they get sort of the safe concurrency type behavior, which is incredibly inefficient, but it's, you know, it's very, very well behaved. This work is asynchronous, so you're on your own for concurrency. UI programs, they can run in one loop, so it's not such a big deal. You're using event handling instead of multiple threads. If you had multiple threads going around, you would have to start adding connections to start to communicate about concurrency, right? So it would be one of the drawbacks in my system as opposed to the Haskell people, which have decided that they're going to make time explicit and deal with the issues accordingly. Okay, so let me move on a little bit here. The nice thing about this system is that we can have, so I try to stick to common syntax here. I'm trying to reuse existing syntax whenever possible, even though I'm changing sort of what they mean in the sense that it's going to be continuous evaluation as opposed to sequential evaluation. But here we have an if-else statement that connects the color of the label. And what this is you can read this as a continuous function that connects the color of label to different colors based on what the current temperature is. So like if the temperature is greater than 90, it can be red. Less than 40, it can be blue, and then otherwise black. But the idea is that we can think of, if you're coming from C++, Java land, C# land, you can think of this as, well, true. You're just running your code in an infinite loop, and each time you go through the loop, you can update the color, no problem. However, there are no loops here. You just write it like that, and you just assume that everything. You just assume that these connections are always being constantly updated, and the way that's implemented is through sort of the event handling interface that the signals provide. Okay, so I just want to demonstrate this really quickly. Really simple demo here. Why? Shh. Never good. So here we have our label, and then here I have the thermometer, which I'm going to control, just modeling as a slider. Up above 90, it's red, and below 40, it's blue. Now what I can do is I can change this program just a little bit. So here's the code. It's a little bit different from what I showed you in the slides, but not quite. I can take the text and I can change it to do Celsius instead of Fahrenheit. And that works. Now, notice that the temperature is being measured in Fahrenheit. So if I move the slider up, we're getting the 90 in Fahrenheit, but it's being translated to Celsius. That's all. So a very, very, very simple program to sort of describe what you can do with signals in sort of the simple sense.
Is there any way to interpose converters signal to convert from Fahrenheit to Celsius without having to change the text of the encoded?
Yeah, I could have added. Well, we'll get into switching later, but I could have added another like checkbox widget, for example, that I could actually do it right now. Well, I don't want to set it up, but because I actually made this example really simple, so it's not easy to change. But you can add a checkbox widget, right? And when it's clicked, you have it in Celsius, and when it's not clicked, you have it in Fahrenheit. And what happens at runtime, as soon as you click the checkbox, it starts translating it. So the other branch of the if statement becomes active.
Right. Here, the way you define this is you connected this to an explicit phenomenon and explicit label.
Uh-huh.
And it's not saying whatever temperature happens to come in, now I'm going to put a new circuit in the middle that's going to do the conversion. And this
Yeah, you.
oblivious to that.
I mean, you could add a way. You could add a way of interposing the behavior. So this is just. For this example, it's just easier to retype temperature twice. You could add something that would translate the signal if another signal was true or not. And but quite simply, that's often just if. So maybe people often want to just write that as if. There's no reason to have an extra component there. sometimes that's not true. Sometimes you need to actually start talking about components that do their own switching. But most of the time, if should be good enough.
We haven't seen much in the way of semantics for the language. I'm curious, can I have more than one definition for text?
Sure. We could.
What does that mean?
So, well, here I have more than one definition for color, right? So color is
They're guarded by.
they're guarded, right? You'd have to guard your definition. You'd have to prioritize your connections, right? You can't have your connections unprioritized.
Here's what I'm wondering. You said before this is like you could put it in a while list.
Mhm.
Let me give you an example where I could have mentioned semantics, but not.
Yes.
Suppose I said, u.text is equal to blah, 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 blah of Celsius dot temperature, and u.text is equal to blah, 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 Fahrenheit dot temperature, where I have two different sliders.
Mhm.
Now, if I put that inside of a loop, whichever one I wrote second is the one that's always going to dominate.
Yeah. So
But if I think of it as a data flow model, and you think it's signaled by change, then
Yeah.
if I change the Celsius one, that changes.
yeah. So this is where the data flow model will starts peeking its head up. So.
Is that what you have?
Yeah, you can think of this as sequential code as long as you limit yourself to assigning variables only once in a path.
Would I be better off thinking of it as data flow?
That's the way I'm going to describe it next.
Is that what it is?
Yeah.
Okay.
There's two different thoughts. You want these languages to be accessible to program. I mean, this language is designed to be easy, so you want it to be accessible to programmers that might think of the code differently. You want to trick them into using a declarative language, basically. Now, obviously it's a declarative language, and any, we all know that, right? But
So is it true that I can write my statement in any order?
yeah, I could switch the ordering but for the else if, right? The if prioritization has to be. Sure.
Otherwise, it's just inputs and outputs.
Yeah. Now there are features in the language that are very imperative where ordering does matter, but I'll get to those later. Signals. Signal is state. Signal is state. So time-varying values, right? They're just basically representing state, volatile state that changes. Yeah. No.
In the sense that, for example, I want to, if I change color,
Mhm.
when I change temperature in different patterns, and I sort of keep a history of how it changes, and then I want to reflect something.
Yeah, you need to use additional components to do that, and you would have to use event handling, which is a different interface from the signal connection. So there are facilities in the language that let you do that, but you have to get away from the nice sort of signal connection model, because now you're actually interested in the control flow of the program. As long as you're not interested in the control flow of how these things communicate, you don't have to do a lot of work. But as soon as you want to know.
I don't think it's control flow, right? It's just, for example, the circuit, you are able to do transformation on circuit. The signal in some sense is a function along the time. Probably your model, it doesn't keep the time, you don't have a precise time concept, but on the other hand, you're at the order of time.
Sure.
Then you can do things like the shifting signals by
Yeah.
something.
So since this is asynchronous, right? We're kind of assuming a sort of instantaneous model, that there's no delay, propagation delay, or anything like that. Now that's not true. Obviously, there's going to be time difference between when an event is delivered and received, but we don't make any guarantees about that. So if you want to depend on any kind of sort of timing in the circuit, you're not going to be able to do that in the system.
Then I guess how to comment in something like it's more like
Okay, I'm not really familiar with the spreadsheets, but yeah, I mean, that's possibly true. But maybe as I explain the language, it become more clear. So let's go back to the slides. So getting back to how you think about this code. So the while loop is not the best, it's not the way that this code works. All these if statements are all compiled into a circuit. And here we show the circuit for connecting the color signal. And just to go through a little bit of the terminology, but the graphics here, that little inverter gate up there, or the triangle, that's a condition. So if the line coming in is true, then it passes through the output coming in from the left. And then the multiplexer or the switch there is it's a prioritized switch. So it takes the highest active output and passes it through to the color. And then the triangle, the diamonds down there are simple greater than or less than conditions. Okay, so let's go through a little bit. So this is how that code I just showed you is actually represented in the system.
So a superglue compiler is actually translating the source code, the superglue code into this.
No. I mean, this is a representation of the rule system that's going on. There's an actual data structure called circuit, but it's just a list of conditions that have to be true to pass through the output. This is just a graphical representation of that. So, so we can have our temperature when it's greater than 90. This, coming up from the greater than symbol is going to be a live sort of signal that's true. And that's going to allow us to pass through red to the color. Now, as soon as that's not true anymore, as soon as the temperature is not greater than 90, we stop passing through the red color through the switch. Okay? So the same thing happens when the temperature is less than 40. We pass through blue. And likewise, if the temperature is not less than 40 and it's not greater than 90, then we're going to just pass through black. That's our default connection. So the switch is completely prioritized. And as soon as it's greater than 90 again, we pass through red. That's how the switch works, this continuous behavior. Now, if you think of the syntax that I showed you, there's really, it's not really else here. Because, else has the semantics as purely control flow. Else is a nice way of specifying prioritized connections, but you can't say if something view.color equals blue, otherwise view.text equals hello. I mean, because you're connecting two different signals there. We can only prioritize within one signal, within one connection, signal connection.
So you're saying that in the code of the different branches, the else, I would have to do this assignment or whatever connection for the same thing.
Or the same things.
Same thing.
Yeah, it's sort of, well, what happens is that if you connect things that are unrelated to each other, I'll let you do that. And actually, you might want to express multiple connections that qualified by one if statement. And then in another else statement, you might specify other connections. But what will happen is that they won't have the else-like behavior that you would expect.
So I think that this is exactly the kind of language where you're trying to make it simple for people, but as you pointed out, you can make a lot of mistakes.
Sure, and the idea is
Check it carefully.
the idea is to have a checker or a type checking system. There's a trade-off here between sort of preventing the programmers from writing programs easily, with an easy type system, and if the type system is too restrictive, they can't do a lot of things that they would want to do. So there's that kind of balance there.
So is it fair to say that in terms of the progress of the language, right now you're at the stage where for somebody who knows what they're doing, you're making it easy for them to quickly connect things. And for somebody who may not necessarily know what they're doing, that's you'll have to add more support.
Yes, but we're going for the latter people eventually. So I mean, the else issue, right, where you connect different signals you connect different signals in else clauses. We would want to come up with a sort of a nice solution that says, hey, you're connecting these things, and they don't really, this connection. There's a connection made in this else statement that's not correlated with a connection made in the if statement, so that's wrong. That's local. That's a local analysis, so we can do that fairly easily. There are other issues too with connections that I'll get into later, but eventually we want I mean, we want a system that's easy to use. That's sort of the primary goal, is to make it really easy to write programs for people that maybe don't even know C.
So a different interpretation for else, I can think of it as syntactic sugar or else not logical disjunction of previous guard.
Yeah,
Right? And then I wouldn't need a notion of priority. Right?
you wouldn't, but that wouldn't work here. Would it work? Well, I mean, I thought about this before. So else in the system is purely a priority mechanism. So there's no disjunction and negation going on. Here there's mutual exclusive. There's already the high branch, the greater than 90 and less than 40. They're already mutually exclusive, right? But there's no way to really verify that. So we don't try. But the problem with the disjunction model is just that you get a lot more connections in the implementation. Sometimes maybe you can't take the negation of the more complicated conditions I'm going to show later don't really support negation. So it's maybe not feasible. But it's another way of thinking about it, and it works for simple conditions, surely.
Have you tried building a hardware system model?
Hardware system model? No, that's not the goal of the project. It's more about building user interfaces.
Actually, that's funny. It's a similar question to what I was about to ask, which is, it looks like your system is a compiled language in the sense that you say, go do this.
Uh-huh.
Chunk of code, go do this. Another way to view this is more interactive, like a breadboard.
Uh-huh.
I put the wires in and things start to light up. You could imagine adding constraints and suddenly things light up.
Yeah.
Do you have that functionality in the way you implemented it, or have you thought about it?
You mean adding like sort of an interactive programming?
Yeah.
Yeah, that's definitely something I want to look at, but it's not something I'm not there yet in the implementation. Probably not going to be done before my dissertation. But it's definitely the way of playing around is you want to add conditions and maybe retract conditions too, interactively, and that's how you basically play around and prototype a system. It's sort of a
And I've got one more question, which is, and perhaps just wait to the end, but still not here. I happen to know how PowerPoint is.
Mm-hmm.
And there's exactly one thing that goes from the model to, which is, I've changed.
Yeah.
That's it.
So
That's the only signal.
yeah. So I mean, definitely for email, this is a little bit, well, for the email example I'm going to use in this talk, right? You have mail coming in, you have multiple views, users switching through views. And I think you have that in PowerPoint too. You have the user. The user is also providing model data to the system. They don't call it models, right? But the user is also inputting state into the system, and the system is adjusting its views of the presentation based on the user input. That would be handled the same way.
Sure. Forward.
Well, see, so there's the MVC abstraction. Usually, they distinguish between input coming in from the data model and input coming in from the user. And in this system, you don't distinguish between that. They're both state. They're both signals. They're both signals coming into the system. But I mean, this is sort of a simplification of the MVC model. I didn't really want to get into it, but so there's a lot more interaction going on inside your program than just interacting with the core data model that the user is interested in. There's also a lot of other kind of interaction going on between components, based on user interaction or just the state of the operating system or whatever. So there's applicability, is sort of an issue too, right? You have to have all these signals to make this language worthwhile. Okay. Sorry.
So I'm wondering, are you breaking down the case too much? Another possibility is just expressing the dependency. If there's no time varying effect, just expressing the dependency using a very simple function language like ML. If I want to write that function dependency, it's a very one-line.
It's true.
Right?
It's
And then what's the benefit? And then over there you have the benefit of
sure, and this is actually the approach that the functional reactive programming people take. Is what they do is they take signals, and they basically take your functional program and you evaluate it at every time point. That's sort of the scheme implementation. And then there's the Haskell implementation is a little bit more restrictive since signals aren't first-class values. But it's sort of that's the principle that began out with. So the functional programming people have done exactly that, and I think starting in 1999. And I think this is a really interesting area of programming language research. It's not just me. Now, wait a second, and I'll get to the object-oriented part, and that maybe become more clear why you would want sort of a circuit system as opposed to a function system.
Yeah, I think at this point we should let you go on.
Okay. So really quickly here, this is basically what the interface for a driver looks like that you would program to if you were writing Java code to implement a signal or to use a signal. So outside in the superglue world, the circuits are managed automatically by the interpreter based on what you've written in superglue code. Now inside the Java world, you have to like use signals according to these sort of simple interfaces, but they're pretty manageable. All right. So now I'm into objects. The problem with the signal connection model, and there are other ways to handling this, but I'm going to do it with objects, is that there's a large number or unbounded number of connections in a program. And this is because we have trees or lists or really, really complicated data structures. And this means that direct connections are not going to be manageable. So the solution I'm going to choose here is I'm going to basically dispatch connections like you dispatch methods in an object-oriented language. So we're going to use the type of the signal container called an object to figure out how its signal is connected. Right? And then the other option is you have a full programming language like ML or Scheme, and you evaluate you have the full power of that language to play around with. And you don't have this issue. You can start abstracting over things like with functions. We're going to abstract over things with objects, and that's going to be the primary difference. Okay? So the infamous class declaration. So we're going to declare our objects via classes in this language, similar to Java or C#. And we're going to have these things called nested classes, and these are very important in this language because there's no way to express an infinite number of connections or an unbounded number or a large number of connections using top-level classes alone. And the idea with a nested class is that I have a tree view widget. It's a user interface tree, and it has a bunch of nodes inside it, right? And each of those nodes need to be connected individually. So what I'm going to do is I'm going to define a node class and says, okay, whenever the tree view widget wants to figure out how a node is connected, they'll just create a node and say, okay, how is this node connected? So in the sense, we're going to have a way of creating an unbounded number of signals in an object using these nested classes. And these classes can be used as types for signals. So these are imported signals, or signals coming in to the object. And we have a root signal, and that's a node. And we have each node signal has a list of child node signals, and they're also nodes. Okay? So there we go. We have an unbounded number of signals in this object now. Right? And model data is going to be this sort of a similar way. We have mailboxes with folders. Folders have subfolders, and the mailbox has a root folder. Okay? So we're describing these sort of not complicated, but large data structures, inside using class system. Okay, so start off with a program connecting a tree view widget called the folder view to a mailbox object called mail. And we're going to start off by connecting the root of the folder, or we're going to start by connecting the root folder of the mailbox to the root of the folder view tree. And then we have to connect all the children of the of the nodes in the folder view tree. And we could try to do this explicitly by expressing each connection individually, but of course that wouldn't work because the tree's an unbounded data structure. So what we're going to do instead is we're going to abstract over all objects of type node in the way that you would abstract over all objects using this. We're going to use these things called dispatch variables to abstract over tree nodes. Okay, so we have this var node folder view.node. And what this basically is doing is establishing a dispatch variable that we can use to talk about how nodes are connected. All nodes are connected. And we're going to combine that with if, the condition again, to say that, well, we have to have a way of reasoning about how Node is connected itself to figure out how its signals are going to be connected. So if we say, if Node is connected to an email folder, then we know we can connect its children, the children of the node, to the subfolders of the folder. Sorry, I always get my connection wrong because I'm left, right, left. We can connect the subfolders of the folders of a folder to the children of the node. Okay? So now we've just expressed an entire tree of connections, of node connections. Because this is going to be applicable for our nodes. Now, as a result of that connection, I have more nodes connected to folders, and then or more folders connected to nodes, and and so on. And I can also express other connections inside here, not just one connection, but I can express an entire group of connections that say, how do I deal with the situation where an email folder is connected to a node, for node objects. Okay. So this is where we get into our maybe more advanced sort of illustration. So the condition symbol is unchanged. We have these dispatch variables, and we're going to model these sort of as boxes with with addition of like multiple boxes. This connection statement, which is a condition, it's basically, this is where I got into the fact that some conditions might not be negatable. Actually, this is probably negatable. I don't know. The problem would be that folder wouldn't be bound if you negated it. We have this connection symbol that says if there's some folder connected to the node variable. So this is another variable, except unlike the node dispatch variable, which was universally quantified over all nodes, this folder variable is sort of created and bound at the same time via a condition statement. Okay, and that's going to capture the folder that a node is connected to. And now, if if this connection is true, we get a valid input. This blue arrow right here is basically indicates that the connection is true, and then we're going to be able to connect subfolders to the children node. Okay, so there's a little bit of rule-driven language going on here. A little bit of, I don't know something like unification, but it's really just binding. It's basically this folder variable. This node variable is sort of like universally quantified, but really it only works for when you're connecting its signals, like a this and an object, which is only universally quantified when you consider how its methods are implemented. And the folder variable, which is basically just capturing whatever node is connected to, whatever is connected to node. Okay, so. Sorry? Mm-hmm. This is the type in the syntax. You have to specify what you want to query what you want to query that node is connected to. Yeah. So if you want to say a folder is connected to node, right? We have to specify the type of that. So it's sort of like a coercion. You can think of it as a coercion, but it's really just saying that node is connected can be connected to something. So what is it connected to?
So node can only be connected to one thing at a given time.
Let's see. Yeah, I'm reversing it again. I always reverse my connection syntax. Yeah, only one thing can be connected to node at a given time. Node can be connected to something else. I mean, you can have connections. They can run a line and then they terminate somewhere. So, like for example, folder is connected. So this is one thing. Folder can only be connected to no, that's not right. Sorry. So folder is being connected to node, right? But nothing can be connected to folder because folder is sort of has a native object inside it, and doesn't need to be connected. Doesn't need to have anything connected to it. So something for some nested objects, something has to be connected to it for that nested object to be meaningful. And for other nested objects like folder, nothing needs to be connected to it. Okay, that's sort of the way of thinking about it. So So what happens is that this rule activates based on other connections. So the first connection made from the root folder to the root node, that creates a node. That creates a node that the root folder is connected to. Okay, and then after this sort of connection is applied, this lower connection is applied, we have more. We have lists of folders being connected to lists of nodes, and that creates more fodder for this rule to execute. Now, this isn't going to lead to an infinite loop, or not necessarily. Depends on the components query the connections on demand. So they say, I want to know what the connection I want to know how children is connected in some node. Okay, they're inside the component implementations. They're going to ask for these connections explicitly. So this doesn't lead to a infinite loop or sort of non-termination unless the component keeps asking for children for node children, recursively. So it depends on the component implementation whether this terminates or not. Depends on what they do with the data. So like when you're building menus, they want to build those menus aggressively. So we'll ask for everything in the tree. So your tree better be of bounded height. But if you're building user interface widgets, they assume that the tree can have infinite height. So we're going to only ask for things when we need it.
Sorry, I think I missed that. Okay, so children and subfolders here are aggregates, right?
They're lists, yes.
So that connection statement, how should I interpret it?
Think of it as connecting a signal of type list to another signal of type list. So there'll be other signals that will be automatically connected under there, and I'll get into that a little bit later. Mm-hmm. Oh, okay, sure. Okay, thanks. All right, moving along. We're going to have prioritized dispatch in this language too. So we have prioritized dispatch. So the language makes connections based on the type of the object, and it prioritizes those connections inside the circuit based on the type of the object. So just like you would prioritize virtual method dispatch in an object-oriented language. Okay. So in this example, we have a mailbox, a UI tree in a table, UI table. We're going to say, okay, when there's one node selected in the folder view tree, and that node and then there's a folder connected to that node, I'm going to connect the rows of the message view table. I'm going to connect the messages of that folder to the rows of the message view table. Okay, that's going to be one connection. All right. This is an operator. Wait, equals up here, you mean? Okay, this is equality, and this is connection. Yeah. It's always been connection in the previous slide. Now, the way I use equals here with these angle brackets is different from when I use it outside the if statement. But they're both dealing with connection, but they're dealing with. Yeah.
Once capturing it, the equal if is like a let.
If is like a let, except it can fail. Right? I mean, if this connection might not be true, right? There could be many different kinds of nodes inside the tree, and so yeah. But otherwise, you could there's a let thing that basically is sugar for if that's always true.
It's actually a lot like a pattern matching in functional languages. You're basically saying, try to match this pattern, and if you match it by this name, then I'm going to compute over that name.
Yeah.
Binding thing, right.
Yeah. Yeah, exactly. It's like first order logic too, without the first order logic. So originally I called this unification, but then I got rid of the unification part to make the language easier. So. Hey, it's great. It's wonderful to find language geeks. Tons of interesting things. Programming language research isn't dead. That's what I have to say, despite what people say. Okay, and then we have a second connection here, which says, for any table, this dispatch variable, again, is abstracting over all table objects and saying, okay, the rows of those tables are connected to an empty list. And so this bracket notation is declaring an empty list. Okay? Now I have two connections to UI tables here. One is making a specific connection to the message view table, and the other one is making a general connection to any kind of table. And that's going to be significant in how these two connections are prioritized. And these can be in different source files, by the way. You probably will be in different source files. Okay? So you get this huge, gigantic circuit here. But basically, what's going on is that there's two connections to this message view table. One is the connection specified to all table view objects, and the other one is the specific connection. And when the size of the folder views, when the nodes selected in the folder view are, when there's only one node selected in the folder view, then, and that node is also a folder, then we can connect all the way through to we can connect the messages of that folder to the rows of the message view table. And now when that's not true anymore, we can always connect an empty list to the rows. And if you look at an email system, when you select a folder, what happens? The messages appear. When you deselect the folder, what happens? The messages disappear. You select two folders. It depends on the email client, but maybe the messages disappear again. And I'll show that. I'll just show that right now. I worked on this all night, but I didn't quite get it to work right. So I'm just showing you some features here. And still,
He was up until 3 in the morning putting together this demo for us.
but I didn't get the progress. I'm going to have to redo the dispatch system, but when I get back. So what happens here is, as I'm selecting the folders, these things are different lists are being different email lists are being shown in the table view, in the message view. Now these messages are totally bogus. I just made them up and randomized them, but you kind of get the idea. Now, what happens here is, now if I select two folders, nothing happens. But if you look at the title, it's changing, right? It's changing. It says, okay, what folder is selected now? How many folders selected, or if no folder is selected, no title. And this expunge button is also changing based on how many folders are selected. So if there's only one folder selected, I can expunge. No folders, two folders selected, I can't expunge because I don't know what folder I'm expunging from. And that's it. Now if we go to the code, it's not as pretty as the last code. It's sort of in disarray. But we have our abstraction over nodes in the folder view to connect their children. We have our abstraction over. We have our connection to the rows of the message view table that are saying, okay, if there's only one row selected, then I'm going to show the messages of that. If there's only one folder selected in the folder view, then I'm going to show the messages of that folder. And I'm also going to set the title to the name of that, to the name of that folder. Now, if there's more rows, what is this doing? Sorry, it's not conclusive here. If there's no folder selected, I just say no folder selected in the window view, and I don't say anything else about how many rows are displayed. And here, I don't know why I wrote that. This isn't necessary, actually, I think, unless I have a bug. And if there's greater than one folder selected in the folder view, then I just title the window, and I don't display any messages in the message view. Right, and that's how this language works. Is you abstract over your objects, and you connect them according to the data you have. And notice that I've combined dispatch of objects with if-else dispatch too. So it's one of the other sort of features of this language is that you can write if blah 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 else blah blah blah, or you can use this type way of dispatching these connections. And most of the time you have to do both. All right. So there's some other issues to like, there's some other features to get in. So we support class inheritance. This isn't really interesting. It's just basically saying we have objects, sets of objects that are related to each other, and we can use that in prioritizing the connections. Okay. Interfaces. Now, this is getting sort of to your question earlier, somebody's question earlier about lists, is we have a way of aggregating, we have a way of specifying, of creating our higher level abstractions using signals. And we can create label abstractions, we can create list abstractions using interfaces, and we can abstract over interfaces like we would abstract over objects. Okay, so we have ways of creating lists, and we have ways of expressing lists, and we have ways of expressing connections to lists. And if you connect two signals of the same list type, then the subconnections are made automatically. So that's why we could get away with just saying list connected to list, because they're both list types, and so we know how to connect their members.
Can you change that? Connect one list with the rest of the other?
Depends on where I'm putting the default rule in the circuit. So basically what happens is that when I've implemented this, I add a rule, I add a connection to the circuit that sort of says, okay, you can connect it this way if this condition is true. Now, if you can get a rule above that, and I think you can, because I think that rule is really low priority, then you can change it. But I don't know if you'd want to. I don't know if you should. I don't know if that should be allowed, actually.
Actually, just following up, I was hoping that the reason that you allow this signals is that you use abstraction to kind of encapsulate this kind of policy. So, for example, if I have two lists, right, maybe I want to do pairwise and order connections. Maybe I want to do n-squared connections. And it seems like I'd like some way of encapsulating that policy.
Yeah, you wouldn't want to encapsulate that policy in a. I don't think you would want to encapsulate that policy in a connection. You would want to encapsulate that policy maybe in a component, because it's a lot more complicated to implement that connection. So I think you would probably have to implement it as a component.
So is that because the component is going to have some extra state to it?
It's not just that, but I mean you would have to interpose a component on the connection explicitly. The component would have some extra state to manage that. Like there's filter components or sorting components, those kind of things. They filter lists, but you have to interpose them on the list connection explicitly. You can't just say, well, if I connect these lists, and automatically sort them, right? And they usually do require state, especially the way the signals work. They have to be they have to be online constantly. So if you have a sorting component, it's actually going to have to basically mirror the list, so it can do sorting in tandem with the list. So yeah, so component that's the role that components serve. All right, some more of the horrible details. Runtime errors. So we've already talked sort of like there's ways of else. You can have you can connect things that are unrelated in else statements, which we can probably fix with stronger type checking. There are some things that we can't fix very easily with type checking, which are ambiguous connections. What if you have two ways of connecting something and there's no way to prioritize them? And if those are if statements, then that's a well-known impossible problem. Okay, and I don't have any easy answers for that except debugging. Sorry, I have everything prioritized that can be prioritized. I didn't give you an example of a connection that couldn't be prioritized. So you could just say X. You can say message. You could say label.color equals red and label.color equals blue on two lines following each other. It's valid, but it's ambiguous. Where is it connected to red or is it connected to blue? We don't use the ordering of the statements in the program to resolve that. So yeah, it's prioritized to the point where it can be, and otherwise it's not prioritized. And you can have and there's a lot of utility in having ambiguous connections. Sorry. No. You want to prioritize things because you know what the priorities are. No, you wouldn't. But like for example, in the first example I gave you, you didn't really need the else statement there between the if greater than 40 or if greater than 90, but you needed it for the default connection, which was connected to black, and you needed that else statement to sort of encompass both of the if statements, and that's why we had the else clauses there. So it's you can definitely express ambiguous connections in this language. And the other one is you can also express situations where there's no way to connect this circuit. There's no way to connect this signal at the current time. So maybe all your rules have conditions on them, and they're all not true at some time when you want to know what the value of the signal is. In that case, you get a sort of message not understood error. All right. So the last sort of feature in this language, it's not really related to objects, but it makes the language complete, are streams, which basically allow you to interpose on events and commands, and it allows you to listen for events, and allows you to dispatch commands, and allows you to iterate over data. So if you look at the signal model, it hides control flow completely from the programmer, and that's great. It hides a lot of complexity from the programmer, but it's not sustainable. There's lots of cases where you actually need to start looking at control flow, and you actually need to expose a little bit of control flow to the programmer. So one thing is, we have buttons. The push behavior of a button is obviously discrete. You cannot model that as a signal, so you model as an event instead. So we have this on statement, which is like if, but it's for events. We can iterate over arrays of data using do syntax. So we have a list of selected rows, and we have this all array signal that basically returns all the elements of the message view table. And so basically what we're doing here is basically just specifying a for loop that iterates over all the messages in this table. And we can perform commands. So we can perform a command that deletes the message. So when the button is pushed, iterate over all the selected messages in the message view table and delete them. That's what this code is expressing. And to note, these abstractions, these stream abstractions, are compatible with signals. But if you're only using stream abstractions in your program, there's no benefit to using superglue. You have to be using signals to actually get a noticeable benefit in this language. The stream abstractions are just there so you don't have to switch to Java all the time to reason about control flow.
Something that converts an array of data into a signal source.
Because you can't, this is actually, the array of data is a signal. It's just an array of signals. And you can't do anything with that, though. You can't connect, you can connect array of signals to array of signals, but you can't test an array of signals as in a condition. At least in the language. You can use components to do that for you if you want. But the problem with array data is that you can't, there's no aggregate operators in this language, and it's not clear what those aggregate operators would look like. So instead, we have separate abstractions. If you're dealing with a list, and you say this list is equal to this list, the all signal is still there, but you never use it. It's used by the receivers of the lists. It's hidden from you. You don't have to use it if you don't want to, right? And that's how we get the signal behavior. We take arrays of data, we package them up in higher level abstractions like lists, and we exchange those between components. Now, what if the components disagree on list abstractions? Now, we hope that they're using the same list, but if they're not using the same list, you have to implement an adapter. Then you have to touch these array signal abstractions to do that translation. You see what I'm saying? Kind of? I wish too. I would totally have. This is my plan at the beginning, was to say everything's going to be a signal, right? That was my plan, and it didn't work. Or everything's not a signal. The problem is you have a lot of behavior in programs that is not representable as a signal. And then expressing that behavior in this language was impossible to do. We have to write all these components to express this behavior, which is just ridiculous. And actually, there's a little bit of, I wouldn't call it synergy, but the compatibility with signals means that I can actually express these on statements and do statements in the context of an if statement, which allows me to get the benefits of signals and not lose them when I have to use streams. Eventually, this maybe I'll talk about it. I'll talk about it now. Is eventually you want to come up with these high-level components that only have signal abstractions. You don't want to be dealing, for example, with buttons, because buttons, they can be pushed. You want to be dealing with forms. Forms can have signal-like behavior, where all the low-level event handling details are hidden from you. But if you're dealing with just an individual button, you have to deal with the fact that the button can be pushed, right? So the idea is, now you have to you focus on the components, higher-level components to get more signals, and then you can hide these details. I'm almost done. This is like I have 3 slides left. So first we have sort of an evaluation, and this was done by hand. So we constructed a sort of a small email client email viewer in Java, and we constructed an email viewer in Superglue. The email viewer in Superglue doesn't exactly work yet, but it parses, and when the implementation is done, it will work. But we wanted to compare the implementations to figure out what the benefit of using this language would be like. So what we did was we compared the line count, and we found that the Superglue program is like 60% smaller when you compare lines of code. Now this is a little bit, lines of code are a little bit bogus because you can take Perl and you can express everything in one line in Perl, right? But it's not going to be useful. So we looked at another metric here for basically counting operations. We took method calls, we took signal connections, we took casts, we took instantiations, something that seemed significant that would have complexity to the programmer. We didn't weigh those complexities. We just assumed that all the complexities were the same for the basis of this evaluation. And it turns out that, at least for this exam viewer, Superglue is only 35% better than Java, which is a significant benefit. But it's not. We were hoping that would be 90%. But maybe later when we understand the language more and we use higher level components, we can get a better benefit. And the drivers, of course, if you want to include that complexity, there's a lot there, a lot of code. But that's reusable between different programs. Oops, did I go backwards? So basically what happened here is that most of the signal connections are simple, and they're not using the if statements to compose the signal connections. There are obvious examples where you can use if statements to compose signal connections, but then there are most of the code in the program is just saying, okay, connect this to this, connect it to this, connect it to this. There are a few compositions, and these compositions lead to really the order of magnitude type of reduction of code. But the problem is there are just not enough of them. We would get more benefits with higher level widgets, as I specified before. So if we can get more signals into the system, then we can get more benefit. And the other kind of point here is that, now I'm shifting to conclusion, is that right now we've only looked at building user interfaces, and I think there's a lot of interesting work out there. I mean, interesting domains that can benefit from a language like this. For example, ubiquitous computing, where you have a lot of volatile data to deal with, and you have a lot of integration, custom integration to do, sort of small integration tasks to get that data to work together. Okay. This isn't a general purpose language, general purpose programming language. So you would only write glue code in this language, and you would only write glue code for a specific domain of programs like user interface programs or not general purpose. Not general, not like Java, right? Not like We actually do have loops. We have iteration, which is like looping, but it's not. It's well, okay. When I say it's not general, I'm not saying it's not Turing complete. I'm just saying it's not meant to be general. It's a big difference, but so we can't do non-interactive programming, and actually, if you want to look at the task of getting arbitrary programs to work in superglue, it's sort of like parallelizing their components to work in sort of interactive ways, which is a well-known hard problem. But it's an interesting problem, and maybe that's the way we can make programming easier, is to try to figure out how we can make our components more interactive. Okay, implementation. We have an interpreter written in Java. We get to reuse Java's garbage collector, which is great. We don't have to write our own. It's not tuned. It's not that fast, but it's fast enough for UIs. Future work, we're going to look at compiling circuits and eliminating unused connections. Because you have a lot of connections there, especially the object-oriented model. You have a lot of connections that don't even apply to your object, but can't be pruned out because we don't know they don't apply. And inlining connection dispatch into Java code directly, or some other language like C++ to make it faster. And a little bit of related work here. So I mentioned the functional reactive programming stuff at the beginning of the talk. There's Yampa and Fruit, which are Haskell systems. They're synchronous. And I think they have problems with connection scaling. They've addressed this in a couple of dissertations already, but the solutions are really ad hoc. There's another system called Father Time at Brown by Greg Cooper. And its system's a lot more scalable. It's asynchronous like my system is. It's basically the differences between these two systems are I'm using a connective sort of object-oriented abstraction as opposed to the functional programming. Now, which one is easier to use, I think, is an interesting question. Yes, the first one has a notion. Actually, the first one is basically arised out of sort of hardware systems. There are actually synchronous languages before these functional reactive programming systems in the late 80s, early 90s that actually had some notion of continuous evaluation. And these systems sort of evolved that into sort of more general purpose programming constructs. Okay, and that's it. So questions or? I don't. Well, I don't have specific reasons about my system yet because the implementation is still buggy, and therefore I'm debugging the implementation as I'm debugging these programs. Now, when it does work, it's just really easy. It seems to me like it's really easy. So this is sort of my opinion. That really to really find out if it's easy, you really have to go to third parties. You have to do a lot of testing, user testing, and it's not ready. It's not ready for that yet. Now, there is research at CMU, John C. Payne. He did the HANS programming language, if you're familiar with that. He basically went, it's a programming language for children. He went to them and he asked them he did a survey, an initial survey before the language began, and he asked them a lot of questions, so found out that people like to reason about programs in terms of events or continuous behavior as opposed to sequential control flow, which is kind of obvious when you think about it, but coming from the viewpoint of programmers used to programming in C++, we kind of forget that. And he actually went through and tested the language, defects and stuff like that. And some of that research is sort of transferable to superglue, but we would have to do a study along those lines too, with probably adults rather than children. Uh-huh.
Where I think over there it's easier to make sure that if I want to connect to some wire, I want to always have something down.
Well, you don't. The thing is, you're not connecting wires there. You're applying functions. You can't. I mean, the people. You can think of a function application in terms of circuits, but it's really not. You have recursion. You have a lot of really powerful things going on there. And it's not, you can say that, well, I can be sure that this is going to happen because I have a function application, but you don't really know what's happening inside the function application. And, or you have to write a complicated function application to do what you want. I mean, I think that's sort of the potential differences between my system and their system. Now that would have to be borne out in, whether connecting things with objects is easier than function application. We would have to do a lot of, it's either a philosophy or philosophical issue with no answer, or it requires a lot of user testing. Oh, sorry.
I'm more worried about the type-based tag over there. How do you really make sure you can cover what you want?
Well, the type-based dispatch, the type-based dispatch is sort of easier than the if-based dispatch. So type-based dispatch, you can specify default connections, and you specify those in signatures that are public, not implementations that are private. So the user has access to all the default connections to reason about, and they don't without reasoning about the implementations of the components themselves. Now the other thing is, like, if you export a signal from a component, then you have to connect it. If the component's not abstract, then you have to connect it. That's simple. Not simple, but it's like sort of, I don't know. It's like you can reason about how imports are connected, but for how exports are connected are completely encapsulated from the user. So you as a component implementer have to either write really good documentation or make sure that the signal is always connected with some kind of default behavior. Okay.
So are you going to use this as the main line of the
This is my dissertation, and I'm.
Are you going to
I'm not. This actually grew out of my previous work, which is kind of hard to see the resemblance now. There's a lot of soul searching, right? Before I had an aspect-oriented programming language, using a logic programming core. And the problem with that is it's not very effective at making programming easier. So I kept extending the abstraction, and eventually I found, okay, this model works really well, and I can get rid of all this other stuff because they don't add anything. And that's what we came up with. So yeah, it's a bit, I have a lot of projects that I'm not writing my dissertation on. So sort of.
Yeah, this is true of many PhDs.
Well, Dawson keeps saying I should just staple papers together and get out.
Yeah.
But I'm like, I really wanted to do something. I really wanted to do something. This is sort of my chance to look at this issue. And once you're in industry, you got to be more pragmatic, I think.
He also wants you to staple it together so you can get out of there.
I don't know. I think that's just his philosophy on grad school. But yeah, Wilson wants me to staple things together too and get out. But everybody wants me to get out. Let's put it that way. Not necessarily. Not necessarily. You could actually like ubiquitous computing, right? It's not very well supported yet with a lot of existing applications or existing abstractions. You could actually position your language into a niche, and there's a lot of niche languages out there, and that can also be a way of instead of convincing people to change what they're doing now, just say, oh, look, you can do new things with this language. And I think that's better, too. You don't want to say this is a better C or C++. You want to say, look, I have these components, and I have this language, and look what you can do with these components in this language. And if people want to start writing their own components, that's great. But you don't have to take the approach of saying, well, we're gonna redo the way you program. You just, it's like do you steal market share from your competitors, or do you create new market share? And I think you can do it the other way.
That's a good note on which to go with
Yeah.
in the discussion. So thank you, Sean. Phraseology. That's a very nice talk. Thank you. So Dick and Amit, I guess, are your lunch crew.